presenciais.
Ok. Sì, poteva prima. Good afternoon, thanks a lot to be here for our section. And I think we can start with the first presentation. Enrica Vecchia e Marco Tutta, integrated with this basic spatial analysis and structural modeling for the adaptive use of the Santa Chiara Dam. Okay.
E fecha agora isto. Estava cheio. Mas tem que ir para ali. Pois. Eu estava a pensar. Não tenho que levar isto. Como é que tu fazes? Não. Onde é que está o rato? Anda com ele. Não dá aqui. Não passo isso para ali. Passa-me para aqui primeiro. Este também. Não, mas ele assim não partilha. Espera. Não partilha. Eu queria era que me passasse os... No, but we need to start online too. We need to share your presentation online. So we are trying to do that. Sorry. Passa-me aqueles dois para aqui. Tem, correto? Sim, aqui sim. Não veio? Veio. Para aí? Ok, agora passa esta aqui para aí. Tá. E agora partilhas aqui, não é? Este. Assim, não sei ver. Vem o primeiro. Ok. Agora. Já está a partilhar, porque senão me dizia só puxar. Não, mas tens. Bem grande. Não, tens para partilhar. Tens para na apresentação. Ele já está a partilhar. É já? Agora precisa de pôr o rato. Queres que eu faça? Aqui. E agora deixa para partilhar. Acho que agora consigo pôr o rato. Como é que está? Okay. Okay.
But I cannot see here.
No,
no.
Just in here.
Okay. It's not.
Deixa eu duplicar. Faz. Dupliquei-te. O ecrã está ali. Is someone online? Mas ele está sharing. Acho que sim. Pois.
Okay.
Thank you.
Okay, good afternoon. I'm Enrica Vecchi from University of Cagliari, and this work I'm presenting concern the integration of GIS-based spatial analysis and structural modeling for the assessment of the adaptive reuse of the Santa Chiara Dam. So the general context of this study is that of rehabilitation and reuse of existing infrastructures. So in this context, we are dealing with a growing demand for sustainable construction and strategies and management. And in particular, concerning historical dams, these infrastructures have complex geometries, structural complexity, and also the presence of submerged portions. All these characteristics make this kind of study very difficult from a reconstruction and direct inspection point of view. So what we did is a multidisciplinary analysis articulated in 3 different stages. The first is the geometric reconstruction of the riverbed morphology, the second, the 3D refinement of the dam structure, and finally, the structural and numerical analysis. Why the reconstruction of the riverbed was so important for our study? Because this starting model is essential to correctly define the dam geometry, also to model the dam terrain interactions, and finally to set the FEM boundary condition and the hydrostatic loads. What we consider is a balance between the coherence of the representation and the data availability in order to produce a transferable methodology for other studies. So our approach is based on the integration of different data sources inside a GIS-based methodology. Our case study is the Santa Chiara Dam, which is located in central Sardinia, Italy, in the municipality of Ula Tirso, along the Tirso River, as you can see in the left image. This dam was designed by engineer Omodeo with the purpose of flood regulation, hydroelectric power generation, and also for the irrigation of the closed Campidano plain. It was constructed between 1918 and 1924 and was in operation until 1998, but after finding some structural issues, it was decommissioned in 1997. Some of the main structural characteristics of this dam retrieved from some historical documents is a multiple arch dam. It's 260 meters long and 70 meters high, and is made of a composite of masonry and concrete. So, starting from the case study, we analyzed some available data set to describe its geometry. And the first one was a UAV photogrammetric survey that was available from a recent study. And it was performed by using a UAV platform, a DJI Mavic 3, acquiring a total data set of around 1,000 images, combining both nadir and oblique viewpoints. It was also georeferenced using 26 ground control points surveyed in GNSS and RTK mode. So as you can see from the point cloud in this slide, this model provides a 3D representation of the visible part of the dam and the surrounding terrain, but it's not capturing the riverbed also, and also the submerged part of the structure, as it's embedded in the optical photogrammetry. So this model was used as a complementary dataset in the following elaboration, supporting the geometric characterization of the structure and the spatial interpretation of the area. Then we went on analyzing other available datasets, some of the publicly available datasets, mostly retrieved from the geoportal of Sardinia region. The first one and the most important is the digital terrain model of the area, which was acquired from an airborne LIDAR survey in 2010. It's a model with 1 meter of pixel resolution, and it's aligned to the official reference system in Italy. But observing and analyzing this dataset, also we assume that it's not representing the submerged terrain, because it captures only the water surface at the time of acquisition. This limitation is also common to other public datasets, because commonly regional geoportals are optimized to describe the terrain and not the submerged areas. And also because standard airborne LiDAR does not penetrate the water, even if there are some sensors able to do this. And since we are dealing with a small water body, there are no bathymetries available for this case study. So as you can see from the elevation profile in the right image on the bottom, the water body is represented as a constant elevation surface having the same height of the boundary of the terrain. So there are no information about the riverbed, and this dataset cannot be used directly. So what we did, the solution that we found was to pre-process this public dataset and combine the processing with some geometric assumptions. The preliminary GIS processing resulted in the exclusion of the water-covered areas. So we separated the part with a reliable height, so the terrain, from the water body. Here you can see the result of the slope map on this clipped digital terrain model, which was the input for the characterization of the surrounding terrain and the support for our geometric assumptions. It should be highlighted that our geometric assumptions are intended to result in a simplified model. So we, as I said, we found a reasonable compromise between realism and data availability. So this is a simplification. What we did was to hypothesize that the basin cross-section could be simplified as an isosceles trapezoid, where the central part is an uniform height value surface, where with only one value of height, that is 50 meters above the mean sea level. This value was the maximum depth that we retrieved from some literature about the dam. So what we did was to produce a model, a raster model, with 1 pixel dimension, so consistent with the LIDAR 1, and also aligned to the same reference system to represent only the central part of the water body. Concerning the two lateral basin sections, we hypothesized a uniform value of the slope, and so it was important to derive the value of this slope. We hypothesized different kind of approaches, and then we prefer to use some known dimensions of the dam, also found in some literature. So we knew the river total width, we knew the central flat bottom width of the dam, and so we derived the two dimensions of these lateral sides, so equal to 75 meters. So having known this value and also known the delta in the height from the terrain boundary to the river and the flat bottom at 50 meters above the mean sea level, we could retrieve the value of the slope to be used for the modeling. We know that this is a simplification, but we think that this could represent these areas without the noise of local topography, which could be derived from other kind of analysis. So what we did to produce a model also for the sites was a transect-based workflow. We extracted the river boundaries from the DTM, and we assigned the value of the nearest pixel of the DTM. And then we produced these transects from the boundary to the reservoir interior, assuming this decreasing of the height with the deduced linear value of the slope. Finally, from the interpolation of these transects, also using 1 meter pixel resolution and the same reference system of the previous models, we produced also raster models for the sites. Then finally, we combined the central model and the sides. We extracted the contour lines to be used in the final analysis. Also handling some problems in the merging, like no data values or discontinuities and so on. And we obtain our model to be used in the following analysis, structural analysis. So finally, after reconstructing the geometry of the reservoir, the next step was the integration of this spatial information into the structural assessment. As we saw, our workflow combines the UAV survey model, the historical documentation, the GIS-based terrain reconstruction, in order to produce a structural model. Our reconstructed terrain that you can see in this part of the slide becomes the essential input for defining the actual geometry of the dam, which was in part available from historical data. So starting from the reconstructed geometry, we developed a 3D finite element model by means of an open source software. The models, as you can see from this characteristic, consist of approximately 1.26 million of tetrahedral solid elements with a maximum element size of 1 meter, which allowed us to accurately reproduce the complex geometry characterizing our dam. Both masonry and concrete were modeled using the Smear cracking model, which is particularly suitable for simulating tensile cracking, while it also preserves the nonlinear compressive behavior of quasi-brittled materials. In this slide, we present the result of the vertical displacement. The maximum vertical displacement is about 1.3 centimeters and is located at the central arch span. Considering the dimensions of our structure, which is, as we said, 260 meters long, this formation appears to be very limited and fully compatible with the rehabilitation requirements of our dam. Another interesting aspect that we can see from this result, and in particular from the figure, is the almost perfectly symmetric deformation pattern. And this also confirms the regular structural configuration of our dam and the consistency of the adopted numerical model. So overall, we can say that our result demonstrates that the structures is able to maintain a high global stiffness under the considering operational loading conditions. Finally, we analyzed the tensile distribution and the predicted compressive stress. The compressive stress remained very low in the overall structures, as you can see from the right top figure. The maximum value is approximately 1 megapascal, and it's significantly lower than the compressive strength of both the materials, so masonry and concrete. And this is mainly because the structural behavior of the dam is dominated by the self-weight of the dam, but not from the contribution of the cloud load. For what concerns the tensile stresses, most of the structure, as you can see from the left figure, remains below the tensile resistance of the masonry, and we have only some localized areas, mainly near the arch to stresses connections and in the upper portion of the dam, which exceed the tensile strength. The most important result maybe of this analysis is that the predicted cracks correspond to the result of the numerical analysis, so highlighting the importance of this kind of studies. Finally, going to the conclusion, we studied the assessment of the potential adaptive reuse of an historical dam. We started from a simplified riverbed model, which was a fundamental input for the following analysis. We used this model to refine the 3D model of the dam available from other data sources, and finally we perform the finite element analysis. Our workflow is, of course, a simplification in most its part, but is intended to be transferable to other case studies, and in particular to some partially submerged hydraulic infrastructures or heritage engineering context where we have to deal with unavailable data, and of course for any cases that require the integration of indirect data and structural modeling. Thank you.
Thank you very much, Marie, for the presentation. I think we have time for one question.
Okay. Thank you very much for this interesting presentation. It's a nice case study. Would you consider, in any case, to use, for example, assessment seismic survey or sonic survey in order to define extractive bathymetry? Because of in cases of the dam, the loads can change a lot because of voids, or in some cases the mud that is against the dam.
Yes, thank you for your question. Of course, this is the preliminary part of the study, but we hope to do some in situ surveys also for the bathymetry. So using sonic MBS. So of course.
How old is the dam?
How old is the dam?
You say story.
It has been constructed in 1918. Mm-hmm. But now there is another one. This is not in use. There is another one here.
Thank you.
Thank you.
Okay. And we change the presentation. Now.
Okay. The three?
Yeah.
Do you prefer
presentation or
PDF?
PDF?
Second presentation is
Tem que passar para ali.
The same. I want to see on the screen.
Ok.
Yeah.
Ok. Partilho já com outro. Sim, mas tenho que depois partilhar. Vê lá se continua a partilhar aqui. Está a partilhar no... Não. Ai, não, mas agora escolha o window. Mas é melhor primeiro fazer isso.
the second presentation. The title is Revisiting Ray Tracing Algorithm for Future Link Spanning Missions. The authors are Francesco Pio de Cosmo and Luca Sderi, and the presenter is Francesco Pio de Cosmo.
Okay, hello everyone, I'm Francesco. I'm a PhD student from University of Florence in a joint program with IAC and IFAC Institute of Senado. The topic of my talk is on revisiting ray tracing algorithm for future limb scanning mission. So, I briefly summarize the project in which I'm involved. The project is called CASIA, and it has the main goal to develop a fast radiative transfer model for the forward model. This for motivated to simulate measurement for the instrument kite. Kite was a mission project that operate in the infrared region of the spectrum, and has the main goal to observe particularly in the middle, upper, and upper atmosphere with a limb viewing geometry. Now, the point is this mission was not selected as Earth Explorer 11. So the main goals of the project remains to develop this code, this fast forward model, and support a future limb scanning mission. This is also due for the so-called limb gap problem. The limb gap problem is referred to the problem that in a few years, satellite with this kind of geometry, like ICCSA or MLS, will stop measuring. So we can have a lack of this kind of measurement in the future year. Now we hope for Strive, that is a mission of the Earth System Explorer that enter to the phase B. Now we can go more into details to as a radiative transfer model work for this kind of instrument. Essentially, the solution of the radiative transfer equation is very simple compared to the instrument in another view looking, because there is no Earth surface effect. So essentially, the radiance, the total radiance observed by instrument is computed as follows to simulate the measurement. We need to discretize the atmosphere in 2 dimensions, and then we have the line of sight that goes to the satellite is divided in a single part based on this discretization. So the total radiance is calculated as the sum of all the emission of each single part with a factor of absorption due to the line of sight, the previous path on the line of sight until the satellite. Now, I want to focus on the more physical parameter of this equation, that is the optical depth. The optical depth encapsulated essentially all the gas properties of atmosphere. It is proportional to the sum of the cross section of the gases with a factor linked to their concentration. This parameter essentially is a function of temperature, pressure, and humidity. But for this kind of geometry, these properties are computed as Curtis-Corson line integral. And the point is that this line integral, to compute this integral in an accurate way, we need to reconstruct in an accurate way the line of sight. And so each single path in this kind of discretization. So we want to we put more attention on this aspect that is called the ray tracing. So how can we compute the trajectory of the line of sight? So for our algorithm, we start using an approach from the ORM used for MIPAS. In this approach, the line of sight is computed using the Econel equation. This equation assumes this form. Essentially, it depends on the refractive index in the atmosphere. So when it is constant, in case without refraction in atmosphere, the solution is just a simple line. so that the trajectory is a simple line. But when we consider a refractive effect in the atmosphere, the solution is a curved line because the line tends to bend due to a refractive effect. So I want to show more details about the refractive index. Essentially, the refractive index is proportional to the air density, and when we see its variability in the atmosphere, we can, as we can see in the diagram, the refractive index is about 1 in the upper atmosphere, but below 40 kilometers, it start to change in a not negligible way. So we want to put more attention on this part of the atmosphere. Then in our code, we implement 3 cases for the atmosphere. We consider a pure geometric model in which we not consider at all the atmosphere. A US standard atmosphere as a constant atmosphere, and then an atmosphere from analysis data of ERA5 that we will consider as the true atmosphere, so with more realistic and time-space dependent atmosphere. So going more into details about the numerical methods, essentially the question was solved in Cartesian coordinates with these adaptive equivalent methods. That is a method that is a compromise between speed and accuracy, because essentially use a variable step size that range from 1 kilometers in the upper atmosphere, so where there is no refraction effect, to 10 meters in the lower troposphere, where there is more atmospheric variability. To initialize this equation, we need initial condition. These initial conditions essentially are linked to the satellite position and the pointing angle of the detector of the instrument. Before the line of sight enters to the atmosphere, the trajectory is a line. So at the end, to initialize this equation, we need to know the point in which the line of sight enter in the upper part of the atmosphere. Now, the point is, compared to a nadir instrument that look directly to the Earth's surface, a limb instrument don't observe in a vertical way, but observe in a tangent way. So essentially, the spectra are not associated with the area or surface on the Earth, but the spectra are referred to the tangent point. Tangent point that are the point of the trajectory closest to the Earth's surface. So the instrument need a certain view angle matrix that associate with a certain pointing angle or off-nadir angle a certain tangent altitude. This is crucial because the instrument cannot know the atmosphere a priori. To do this choice of these pointing angles, you need some kind of assumption or approximation, because essentially we need to know a relation between these pointing angles and this tangent altitude. So the geometric aspect linking to the Earth ellipticity or the orbit can be accounted in advance. But for the atmosphere, we need to do some, the effect of the atmosphere that bend the line, we need to do some assumption. For example, in the case of ACE, FATS, or MLS, the estimation of these ordinary angles is made with a pure geometric model, so without considering a refraction in atmosphere. While with MIPAS, this is done with a constant atmosphere, the US standard atmosphere. So now we want to look more on this aspect linked to this model. This because as we see in the few slide, in the another slide, an effect on the trajectory propagate also on the computation of the radiance spectra for the instrument. So in this slide, we look more in details on this displacement. Essentially, we look for four specific nominal tangent altitude, and we see for an entire orbit, and we look for, in the case of using a geometric model in the dashed line, or a constant US atmosphere in the solid line. So when we use of Nadir angles with this model, we can see that for the geometric model, we can have also 1 kilometers of difference of the true tangent altitude and the tangent altitude reached with the of Nadir angles computed with this model. While for in the case of constant atmosphere, the displacement is lower, is up to 100 meters. Now we look more in details. We look to all the tangent altitude below the 40 kilometers. As we can see, essentially, when we go in the upper, in the more we go to the troposphere part of the atmosphere, and the tangent altitude displacement increase, because in this part of the atmosphere there is more atmospheric variability. So we explore and we check the error that we commit on the altitude aspect. Then the problem is also a two-dimension problem. So we look also on the horizontal displacement for the same altitude. As we can see, there is also displacement on the horizontal part of the tangent point, and with a constant atmosphere, there is a displacement up to about 6 kilometers. Then we check also, we discover that there is also a correlation on the seasonal effect, because we discover that if we look in the north hemisphere, on the south hemisphere, in different seasonal conditions, for example, summer or winter, we look that there is a different displacement in this error. So, to conclude, we starting to updating the ray tracing algorithm proposed using Kite mission as a case scenario. Then we quantify in a detailed way the displacement effect due to use in a different way the atmosphere refraction, and so we evaluate the errors due to horizontal inhomogeneities and also seasonal features. For future work, we think about that machine learning approach that can be trained on representative climatological dataset can encapsulate this spatial seasonal variability and can improve in a better way this displacement and so the ray tracing initialization. So, thank you. If there are any questions.
Okay, thank you.
Okay.
Francesca?
Okay, the next presentation is active reflection and passive formal reflection. The formation modeling using the CSR methodology, some remarks for Sentinel-1 imaging tests.
We know from the
Better fidelness in the
Cigao.
Cigao, grazie, perché Cigao non l'avrei mai indovinato.
Exactly. Well, just this one, please.
Okay.
Well,
Wait a moment.
move from the limb to heaven or hell, because in our situation, the technology we use, which is sun interferometry, can be two different choices, but not limb. Or you can or cannot measure. This enough a specific topic, because we are discussing like I show you the reliability of some ground points made for interpreting synthetic aperture image. It's very important. Usually, you probably know that a radar image, a macro image, is not so straightforward in terms of algorithm. The understanding of an image can be difficult, and so sometimes you need some points for calibration, radiometric calibration, and so on. But in particular, in this case, we are talking about interferometry, where you measure using more than one image, a set of star images, to detect the deformation of a large area. And interferometry works only when you have some condition. Well, let's start. Just the main actor of this presentation is the Sentinel, which is a satellite which includes Sentinel-1, which includes a synthetic aperture reader by ESA. It's a very, very good tool. Well, I will give you some small details. Just an outline of the presentation. I will try to explain for who are not familiar with the synthetic aperture radar. These are the technique, how it works, which are the main points. What is a passive and active reflector, the pros and cons of these two choices, and then we show finally the results of our instrument, our device, and to take some final remarks and conclusion. The Sentinel-1 is a very famous satellite from ESA. Is a lot of advantages. First of all, it is a synthetic aperture image available for free and with the release time strictly maintained. So with the last glance, we can have a 6-day or release time. This is very important because interferometry is possible only if the image maintains a statistical correlation. So if you have a lot of time in between two different acquisitions, you lose information. And this occurs in different ways. The step backward, what is a star image? A star image is just an image when we associate one pixel, a position, an amplitude, and the phase of the radar signal, which is the radar base scatter from the surface. It's not, sometimes can be similar to an optical image. In this case, for example, you can see the image of Barcelona, where the bright points are urban area, whilst the mountains and the vegetated area give a very lower response. For this reason, we can classify some different bands reflect and good reflector. Bad reflector, vegetation canopy, the agricultural fields and so on. Good reflector are building a specific passive structure, which I will explain later, or active sensors. What is important is very good about the interferometry that we don't talk about the phase of a single image, but we have to evaluate the differential phase, because the information is in this differential. But how it consists? The basic product of interferometry is a single interferogram. Probably you are familiar with this kind of image. Unfortunately, for example, from the last quake events, because it's the faster way to understand how occurred the deformation in between the before and after the seismic events. From the measurement point of view, in the simplest case, we can associate a variation of the line of sight distance, that I call the geometrical variation of the interferometric phase, to the distance. Lambda is the wavelength of the signal, and so it is less constant parameters of the data. You have to consider that usually, or not usually, always, the satellite never pass in the same orbit, because it must cover all the surface of the world. So you have a component of the geometric component of this different position. It's very important to underline also that we took the formation bar, we measure the line of sight component of the formation. This is the limits of interferometry. You can use, for example, descending and ascending orbits, because they have different geometry to make a composition of the two components, but it's not ever so enough. Well, the main advantage of the use of SAR imaging and interferometry is that you can have this comprehensive spatial and temporal information with respect to points wise information. Not invasive, can penetrate clouds and whatever is mostly individuals, mostly, because if we talk about amplitude, the effect of atmosphere is negligible. But in case of atmosphere, no. In the case of the interferometry, no. And this is the main problem. It is well, very famous. Here you can see some, including a cover of natural image on earthquake. You have to consider that being this an interferogram, more dense are the fringes, the stronger, the higher is the displacement. And this is depends also from the parameter the wavelength. By the way, in this case we use only one satellite, so one frequency. Unfortunately, at least the hell, not the heaven, we can obtain information about the displacement, which I call a movement, but very often we have to take into account of other terms. The term of topography, which can be usually can be negligible, because we can know the position of the baseline. The baseline is different position between the two passages. We can know with a very high accuracy from ISA, and also if we have a very good digital elevation moment of the surface. Then we have the noise of the instrument, but usually it is negligible. But there is a component which is due to the target. If we observe from the electromagnetic point of view surface where you have changed the humidity, the plant has growth or has moved in another different physiological moment, it will change a lot. And finally, the atmosphere, because the atmosphere, as happens in the case of lead sounding, in that case it is exaggerated, because you want to have information about the atmosphere, but not here, where atmosphere is the problem. So we have to take into account that you can find variation of the phase due to the variation of the temperature, especially with water vapor. And we are talking of the first layers of a troposphere. Fortunately, there was the Polytechnic of Milano and then other companies developed a very reliable algorithm, which is called the permanent scattering techniques. It is a technique based on statistical calculation, where if you consider different data, different position, you can consider that there are some points which are called in permanent scatter, which maintains coherence, maintains the possibility to calculate with the statistical relation of the phase of the signal. And so in this case, considering the delay in this, interferometric phase in this point, you can evaluate also incorrect in the other point. But it's actually only for some points which respect some statistical condition. And the idea basically is that if a point is very bright and stable, in amplitude it's useful also for phase. But not always you can find this point because there is the problem that there is vegetation and so on. Just to give you an idea of how operative is this in interferometry, this is an example of the European Geological Monitoring Service. It's a tool developed for Copernicus. In this case, you have a map of all Europe, most of the Europe, and for each point, you can have a temporal series of the deformation. This is very useful for application, but not always this is possible, and so we need to sometimes to put some reference point in the glacier, for example, in an area covered by vegetation. And there are two approaches. Well, the first, which is classical, is to put a passive reflector. Passive reflector is simply a target with a geometry and a metal structure with a geometry which is very bright, like a prism in optical view. It is it main advantage is that it's very stable, low cost basically, depending on the wavelength, and easy to design. But we have to consider that sorry, this is lambda. That according to the wavelength of the radar signal, the size of this passive reflector can increase a lot. And at C-band, for example, Sentinel case, to obtain hopefully a 0.1 millimeter accuracy for this reference point, you have to build a reflector with the size of 1.2 meters to install this object in a glacier and other places not so fine. So the passive reflector has the problem of very difficult installation. Sometimes with no wind, it can be wind sensitive because the structure, if we are looking for sensitivity below 1 millimeter, of course, if a strong wind, the structure must be very, very hard. Otherwise, you have this vibration too. And it provides only one single polarization, which is another parameter of the radar observation, which is very important. The idea to use an active refractor consists in substituting, let's say, the geometry with the amplification in an external source of energy. In this case, we have a receiving antenna, which is basically a very simple analogical transformer. There is an antenna which receives the signal from the radar, amplify it with filtering something, some factor, and retransmit it in the higher power. So you can obtain strong signal, but so you have a very compact PC. Imagine that this is our 50 centimeters, is our last prototype. Very a few, I think that it is 2 kilograms overweight. The main advantage is the cost can also be reduced because according to the technology, microwave technology is becoming more and more cheap, and you can. It is all the only solution for a lower frequency because if you increase the wavelength, you cannot install such an object in another case. But unfortunately, first of all, it's power consuming, so you need a source of energy. A solar panel, a battery is sensitive to temperature, not the temperature of the propagation, but its temperature because it's an electronic device, and any electronic device needs to change. For example, in a place where temperature change from 10 minus 0 to 40 degrees, the electronics suffer this, and also especially phase can change a lot. And the cost can be reduced a lot according to the development, which are technology and so on. Here is an example of a test. This is an installation in a lens light in Andorra, where you put several passive corner reflector and an active corner reflector just to monitor the lens light. Here you can see just some picture about the installation. But going straight forward to the most important things, if we observe an image of this installation, you can see that we can detect the single current CR are the passive current factor and AC is the active. You can see from this basic image that the signal is very strong, so we can obtain a very, very high signal. And it is very easy to find, because if you, for example, now not, because I think that the battery there, the project finished, so we are not. But for 3 years, you can go to the ICCSA Sentinel Hub website and check if your right, so if the device is working. If you have the responses. In this case, let's say the basic test, if you put the passive and you switch on and off the active, you obtain a very strong, two different times, of course. The features of this observation. These are two plots. The amplitude sigma 0 is the typical investigative coefficient, which is the parameter usually used for evaluating the amplitude of the radar signal. Here you can see the phase transformed in millimeter, according to the simple formula. And you can see that here we are talking about 3 years, almost 3 years time. And the data are very, from our point of view, very good, because let's say the amplitude maintains in a set of value which correspond to a stability of the deformation good enough for us. Of course, we are not talking about a geodetic computation where you need an accuracy millimeter or less. But if you consider that we are talking something which can be a tool for lens lines, a millimeter sensitivity and millimeter accuracy, a few millimeters is enough for a hydrological study and or just for monitoring this situation. So, of course, this data have been compared to other to the experience of other researchers. In particular, this is another of this device developed by a company, and basically we obtain very similar results, because in the first paper to dates 2014, they obtained 1.8 to 4.0 millimeter. So they finally assessed that a compact lightweight alternative to common effect. This is a very strong statement. Same occurred with other results. We basically obtain, we have two main studies. Before the installation in the field, we make a very strict and hard laboratory test. And the main outcomes are that effectively, actually, you can have a millimeter accuracy over time till 2 years lapse. All the other authors also confirm that the main issue is this dependence on the temperature of the device, for which, for example, in our device, we include a sensor inside the device, because so you can have the data, the temperature data corresponding to the satellite acquisition, and so to make a statistical correlation using directly the data on field without just to conclude this talk, I want to underline that now they are working new mission, satellite intercapture mission, working at lower frequency and so larger wavelengths dedicated to other applications like biomass estimation or humidity of the agricultural soil. In this case, of course, this option will be unfeasible. So let's say this line could be more and more profitable if you apply it to this kind of mission. And that's all from my side.
videos where you are very explicative. Presentation. We have time for input. Okay. Your presentation.
You mentioned about accuracy, but did you manage to combine the result with that of a GNSS? Because this could be helpful also to transport from the line side to the local.
In the papers refer to this campaign in project in Angola, yes, where you can see in one of the pictures.
Okay.
We have this, of course, we need always a reference point. And usually, passive corner are also used to make a cross comparison. And I didn't make the question before for your presentation, it's very interesting. The technology was born in ground-based application for dam monitoring in 1999. The technical system.
Very much.
Okay, thanks a lot.
Thank you, Guido. And the next presentation is a robotic GPR pipeline for automated surface analysis in multiply scenarios. Therefore, I know the classical method, the business idea, to sign and Vega Perez and speakers. Okay.
Good afternoon. Thank you very much. This is the guideline of our presentation. I wanted to explain just a little the motivation. We are working with GPR. GPR is a non-destructive geophysical method, the geophysical survey, that is based on the emission, propagation, and later reception of an electromagnetic wave. That wave is reflected on the surfaces that separate media with different electromagnetic parameters. That electromagnetic parameters are mainly resistivity or conductivity, of course, and the electric permittivity. The shape of small targets are like this. Are quite like this. They see pergolas. But what are the problems with GPR? We have two main problems. One of them is that because it's very time consuming. We need an operator that moves an antenna along a surface and obtaining data. And the other one is that it is required an expert that define what are in this kind of image that are the B scans, what are the target, what each one of these images are related with. Then we find a solution, a small solution. Okay, that is. For if we are, is it time consuming? What's the solution? A robotic platform. If we put the GPR on a robotic platform, it takes data, and it's not necessary an operator, a person that is moving the antenna. And what happens with interpretation limits? Then we can use artificial intelligence or radar or automatic pattern recognition. Then my colleague will explain what are we doing in that project.
So the GPR can have very different sizes depending on the application. It can be this huge, or this small. So the robot depends actually on the application. Our Center of Research has created two different robots depending if it's for agricultural things. It's a robot like this, it's omnidirectional, it's autonomous, and the antenna is back here with frequencies around 200 and 2000 more or less megahertz. And for construction purposes or deconstruction purposes, where the GPR is really, really small, the GPR is normally attached here in this robotic arm. And this is the second robot that we have developed with almost 3 meters height of acquisition. And in this case, we use a multi-frequency antenna, which has more resolution but less depth. So yeah, going to the solution and the AI mathematical background that we have to construct, we have the robots, which is the unified pipeline that all the robots and all the GPRs have in the back. So there's a shared backbone, let's say, for all robots, for all antennas, which is first a radiogram standardization and then an hyperbola detection. And this other part depends on the specific purpose of the application. So let's move to the radiogram standardization. As my colleague was saying, radiograms can be sometimes complicated, so you have to standardize and increase contracts among other things. So we can move from this radiogram to this other one. And then we want to detect these hyperbolas. So we use a computer vision model. Actually, I think this one is with YOLO, but we also try with ResNet and CNNs in general. And we can see here that actually all the hyperbolas are being detected automatically with these parameter precisions, but we have already increased these parameters, which are pretty high. So we are really happy with these results. And this is the shared backbone. This means that all robots, the two of them, use this shared backbone, but depending on if it's for agricultural or construction purposes, we have a specific domain analysis. If we move to the construction part, once we have already detected the hyperbola, we do a geometric translation. We turn these hyperbolas into actually a real hyperbola with all the mathematical behind that hyperbola. So we can estimate the position and also the depth of the hyperbola. And once we have that, like here, we can see like the hyperbolas are being automatically detected. We can also know if these hyperbolas represent a metallic or other material, normally plastic object, varied object. And for that, we use a very simple backbone with Fourier transform analysis. If we do a Fourier transform of this, in which these two hyperbolas correspond to metal pipes, and these two correspond to plastic pipes, we can see here that the energy related to the Fourier transform are way higher on the metallic pipes, and actually in the plastic pipes, there's no peak. So that's how we know if this hyperbola corresponds to something that is highly metallic or not. And when we did a statistical analysis with plenty of hyperbolas, we saw the same we are seeing in this spectrum that the plastic has a way lower energy than aluminum or steel objects. If we move to the agricultural application, we are normally interested in finding roots, like agriculture people want to know what's behind the trees. So again, with all those hyperbolas that are being detected with computer vision, we created this kind of, I would say, integrated program where you find a peak response in yellow. It means that there are a strong hyperbola in that place. So we did a survey, a circular survey. We excavated the tree to find the roots there. And what we found is that the zones that are with higher amplitude, that means more yellow, are actually the zones that has more roots that we found when we were excavating. So again, the GPR demonstrates to be a good sensor to find things that are underground. However, we are working in more, we call that the next generation of analysis. Again, for agro, we are also interested in knowing if the GPR can help with soil moisture identification. This is a mini example of simulated data. That's why it's in future. We have not tested yet this in field. But what we can see here is this is
like the Fourier transform, and not that pi is peak instantaneous amplitude, which is a parameter of the parallelograms, which is correlated, we would say, with the contents of water. These different colors mean the variation of the soil, because the soil doesn't have an homogeneous content of water, so depending on the zone, it can have more or less. But in any case, we can see a positive, strong correlation, and we are still further investigating that. Moving again to the construction application. This is a Pladur ball. I don't know, all of you know what Pladur is, but it's a cardboard ball. You can see here that the diagram is very homogeneous, and this one is a brick wall. So we are investigating if in an automatic analysis we can differentiate two different kinds of walls, again for construction and reconstruction applications. And moving to the conclusions, we show, I'm sorry, these were two videos, I'm sorry that you cannot see them in this PDF format, but again, yeah, we have found that the robots are able to do repeatable GPR acquisition. On the other hand, we have shown that all the pipelines that we have been working on can be really useful to detect underground things. However, our third conclusion is that we have still to merge both things. We have the robot working on its own, and we have the backbone working of its own, but we have still to merge this. We are in a preliminary, let's say, beta access. This is, like, you can find this in the paper. This is the summary of all the pipeline that we have done here. The GPR, the two robots, all the shared background, in red, that analysis that depends on the applications and the different outcomes that we have been talking about. Given said this, thank you very much in the name and behalf of all my colleagues, because we are a big group. Actually, this is just a group who's working on the sensors of the robots. But yeah, we are quite a big center of research. Thank you so much.
Thank you, Gloria.
Any questions?
Any question? You say that between metallic and plastic pipe, you see obviously a difference of energy of structure. But did you study the difference of the first phase of dynamic content of the signal switch from metallic and plastic?
We did, and we know how to do that in laboratory or manually, but we have not found a way to do it in automatic pipeline. We have found errors. Yeah, it's more difficult than calculating a Fourier transform. But yeah, we know that there are differences. If it's metallic, you have a shift, and if it's plastic, you have another shift.
So this is the first way to reconstruct, to reconnect the different type of pipe.
You're right. You're totally right. We didn't find a way to do it automatically.
Thank you.
Thank you so much.
And the last one is the second one. Now the last one presentation is always Rita Vecchi, with the assessment of local regions performance Antonino Pala.
Só quando eu coloco isto, vai à vida. Não, está bem. Já consegui.
Thank you. Hello again. This study concerned the assessment of low-cost GNSS receiver in urban environments. So we are dealing with GNSS technologies, which is known to be to range from different application fields, from navigation to surveying, reaching also high precision positioning. Also, the accuracy range from the meter to the sub-centimeter level. And commonly, when we refer to high precision positioning, we refer to geodetic grade instruments. So the instruments able to provide high performances, high reliability, and also associated with very high cost, ranging from 10 to 20,000 euros. But recently on the market, there is the availability of low-cost devices, which initially were developed only based on single frequency acquisition, but now they are able to acquire multi-frequency, multi-constellation, and also they are able to support RRTK and un-RTK modes. So due to the relevance of these new kind of devices, there are many studies to demonstrate their performances in open sky or rural environments, but there are few studies in urban and obstructed environments. So what we did was the assessment of the performance of these devices in two scenarios, representing a semi-open environment and an obstructed area. We compared the low-cost instrument, which we called in the following images and slide the LC, with a geodetic grade named GD device, and we assessed many different quality parameters. So going to our low-cost device, we selected a U-Blox ZF9P receiver together with its patch antenna, and these are some technical specifications. So as you can see, the receiver is able to acquire multi-band, multi-frequency, so L1 and L2. It has a nominal declared accuracy in RTK mode of about 1 centimeter, and it's developed together with its antenna, not integrated. And the cost range from 150 euros to 300 euros for the receiver and 100 euros for the antenna. As it emerged from this slide, what is developed to the user are only the sensors, so the user must assemble all the sensors ad hoc. So what we did was to produce the housing for the receiver, the aluminum mounting ring for the antenna, and the disc for the antenna also. Also, we had to buy an Android-compatible device in order to control the receiver, and we used an open-source software also to stay in the lower cost, which is named SW Maps. The situation is very different when we refer to geodetic grade receivers. So we have, in this case, we selected the Trimble R12 device, which is a multi-band also acquiring L5 frequency. The declared accuracy is at the millimeter level, millimeter, half centimeter level, the nominal value. And the instrument is totally complete, so it's given to the user with an integrated geodetic antenna and a Trimble proprietary software. It costs around 20,000 euros. Coming to our study area, we perform our test in the Faculty of Engineering and Architecture of University of Cagliari. As I said, we selected two scenarios, a semi-open area named ST1 and an obstructed area named ST2. The first one is an area where we have buildings, surrounding buildings, but only sparse tall trees. So we have a quite good sky visibility. While in the ST2, we have a very dense tall vegetation and buildings at a greater distance. As for the experimental setup, as you can see here and from the right images, we in both the environments we placed two very close points, only 70 centimeters of separation in order to place both the tripods and both the instruments simultaneously. As for the quality control aspect, we evaluated two parameters, the carrier-to-noise ratio and the multipath effects. The first one is known to be an indicator of the signal tracking quality, and it's also known to be generally lower for the low-cost devices. For what concerns the multipath error, it is due to the combination of direct reflected signals, and so it's strongly environment dependent, and it leads to significant degradation of positioning accuracy. From literature, it is also known that mitigation effects are mainly bounded to the antenna design. Professional antennas, like the ones on the right, choke rings and so on, lead to reduced multipath effects, while low-cost antennas, as you can see for sure, doesn't have the integrated ring, which reduce the effect of the multipath. Here there is the description of the static sessions that we performed. We performed two independent measurements for each environment, 2 days apart, switching the position of our instrument of the tripod, and we have a total observation interval for each session of about 4 hours. I didn't mention it earlier, but in this image you can see also the location of the reference of the permanent reference station UCAG that we used to compute the baseline. Due to the very short distances we are dealing with, these are every baseline is a very short baseline between below 1 kilometers of length. This reference station is part of the European Permanent Network. It is also operated by ASI, the Italian Spatial Agency, and is classified as a Class A station. For the static processing, we used RTK-lib software with the processing parameter you can see in the bottom table. Finally, we also did two NRTK sessions, only using the low-cost device. So we choose only one representative point in each environment, and for the correction we used the SARNet network, which is the regional network for NRTK correction in Sardinia, which provide coordinates aligned to the official reference system. For what concerns the acquisition strategy, we acquired very short duration sessions of about 5 seconds in order to reproduce real operational conditions where we have very short acquisitions. But in order to understand the possible temporal variability of the solution, we acquired the same position at regular interval of 15 minutes. So we had 17 different positions, observations for our NRTK sessions corresponding to the same point. Now we go to the results. The first one, as I said, is the carrier-to-noise ratio. In this slide, you see the carrier-to-noise as a function of the satellite elevation angle for the geodetic device on the left and the low-cost device, and for the two different environments. But maybe it's better to go to the statistical results. We classify the result into 3 categories. So the first is the impact of the receiver quality. we see that the geodetic device exhibit consistently higher values of the signal to noise, of the mean and the median. So it results from the better signal quality associated to this device. While for the low-cost device, the values that are higher are only the ones of the standard deviation. So we have a higher variability and a more sparse distribution for the static sections. Concerning the impact of the environment, we see that there is a clear degradation from the ST1 to the ST2 for both the devices. And so, the effects are more pronounced on the low-cost device. Finally, the frequency band, the computation using only L1 leads to higher values than L2, so this proves the better quality of L1 frequency. Here we have the same results, but for the multipath effect. So on the left for the geodetic device, on the right for the low-cost device for the two environments. Some results are already visible, but we go to the statistical result once again. Going to the impact of the receiver quality, we have higher values for the low-cost device, like 2 times the value associated to the geodetic device. And the main cause, as we said, is related to the antenna. So the low-cost antenna is not providing a good reflection, a good attenuation of the multipath effect. As for the environment effects, we have a strong increase in the values for both the devices, going from the semi-open to the open to the obstructed area. And finally, we have not a very significant impact of the frequency band. Only minor effects are visible only from the statistical result, but not from the images. For who is more inside this kind of studies, these values of the multipath are not very common because we are dealing with a semi-open environment. So commonly, if we have favorable conditions, values are different. Then we evaluated the statistical positions results. So we evaluated the accuracy of the position from the low-cost device compared to the ground truth that was the reference position obtained from the geodetic device. So here in the slide we have the difference in the 3 components, in easting, northing, and height, the resulting horizontal error and 3D error. And also we evaluated some quality indicators that are the solution quality indicator and the satellite number. What emerged from this data is that in the semi-open environments, we have an accuracy, so the difference in the 3 components at the millimeter level for the horizontal components, while we have an accuracy at the centimeter level in the vertical one. The resulting positioning error is also in the millimeter level, while the 31 is at the centimeter level. So we have a high agreement between the 2 devices and good performance, we can say, in the semi-open area. Things change in the obstructed environment. We have the northern component that reach the 1 centimeter level. Also, the height component increased by 3 times, and the same for the horizontal error and the 3D error. So we have a decrease in accuracy in the obstructed conditions, and the vertical component is always the most affected. What else we can say about this result is that looking at the number of satellites and the quality indicator, you see that the quality indicator is always referring to fixed solution. So we cannot say that fixed solution ensure a good quality in any case. And also we can say that the main reason of the decrease in accuracy is due to the multipath effect. Finally, we go to the NRTK performances that we assessed in two different ways. So once again, we compare the mean of the coordinates from the NRTK observation with the ground truth, and we can say that there is a good horizontal accuracy in the semi-open environment and at the millimeter level. For the height, we have 6 centimeters, but it's in line with the expected accuracy of the method, while in the semi-obstructed area, we have the same for the eastern component, while the northern component and height component increase by 2 times or 1.5. Finally, the final results is the observation of the time series of the NRTK solutions in order to evaluate the temporal stability of this method, which can be seen like the repeatability of the coordinates over time. Here you can see the time series of the 3 components, easting, northing, and height for the semi-open environment and the obstructed area. Also, the satellite news are represented by the green bars, and the mean of the solution is represented by the red dotted line. What can we say from this result is that in the semi-open environment, there is again a good stability where the sigma values, so the standard deviation of the NRTK positions, are around 3.5 millimeters and 5.8 millimeters for easting and northing component. The residuals, we meant by residuals the differences of each solution with respect to the mean one, are generally within 1 centimeter, so the stability is very good, but there is a higher variability for the height component with a sigma around 1.4 centimeters. What happens in the obstructed area is that the horizontal components reach 2 centimeters, 1.5 and 2 centimeters of sigma values. The residuals are generally within 4 centimeters, and the vertical component increases its sigma value by 2 times. For the satellite number, we didn't find any correlation because the number remained quite stable in the 2 environments and in the 2 time series. I move to the conclusion. So we evaluated the strong potentials of the low-cost receivers for a high precision application because we stay under in the millimeter level for the horizontal and the centimeter level for the vertical components. Especially this kind of instrument can be used for surveying and geospatial fields. The performance we saw that are strongly dependent on environmental conditions because the performance are very, very good in semi-open environments and open, of course. And as for future works, we intend to extend the NRTK analysis also to kinematic acquisitions, to test other antenna receiver combination in order to perform the better configuration possible in low-cost stuffs, and finally to optimize our GNSS configuration. Thank you.
we are in this room for the next part of the second part of the section about for okay, after the computer. I don't know. I think that
Olha, já posso mandar estes todos para o lixo?
Sim.
Onde é que está o lixo?
Martina, okay. Five.
I am the only one.
The next is virtual. You.
Okay. We are just trying something. Then we'll help you.
Ok.
Ela quer para a apresentação.
Quer por já? Ok.
Eu? Italiana. Eu falo um pouco português.
Por isso que entende.
Esta?
Sim.
Podes pôr só essa. As outras são todas online.
Me sale bien paper, si todo mal paper, si todo no.
Colocaste a
Oye, creo que vamos a
Pode ser a primeira.
Achas? Acho que sim. Se calhar a primeira é minha, que eu pus primeiro ou não?
Então, pronto. Experimenta. Desligou.
Desligou. Não, está certo, desligou a dela.
Ok. Sim.
Olha, então pronto, estava ao contrário, mas acertamos. Ok. Pronto, então teríamos que ir.
Ok.
O que é que tem no chat?
Ela estava a dizer, mas não estava a temperatura.
I don't see the video
Áudio
on GTC. Could it do it with a two session on another Firefox window?
que é?
Hello, I don't see the video audio. Ele não conseguiu ver.
Mas estava a partilhar bem.
Estava.
Nós agora estamos a falar, então sei. É assim. Cala isto.
So, good afternoon. I don't know if the speaker is here online. The share. Luca, we can start if you want.
Hi, Luca, are you there? Hi, Luca. Luca, can you hear me? No.
No.
No, Luca.
Ehi Luca, non ti sentiamo.
Sarà ora per tutti.
Ok. No.
No.
Ok. Tanto aspettiamo il rientro dal coffee break, cioè dall'aula, quindi abbiamo qualche minuto. Ok. Prova, esci ed rientra, ok. Ok. Ti richiamo, ciao. You can try to
Out and
reconnect, yeah.
Okay.
Marina, questa Monica.
Acho que não.
Monica.
Ok.
Ok. Questo è come... Ah, è pure the first presentation, Luca Pirotti. Forse.
Ah,
It's
ok.
the first, yeah.
Ok.
Il prossimo. No, Luca non si sente.
No.
Lui non si sente, ma gli altri si sentono. Perché deve essere un problema di audio.
Marilena Cozzolino is connected. Marilena?
Sì.
Ciao Marilena.
Waiting that Luca solve this problem.
Yes, we can try to reconnect with the Luca. But we have another 5 minutes because people are in the coffee break.
Okay, perfect.
So we try. Otherwise, start your presentation after with the Luca.
Okay.
Luca. Luca reconnected.
I don't know. Wait.
Luca Pirotti?
Ok.
Luca? Ehi Luca?
No, non mi sente per niente.
No.
Io non capisco, perché poi adesso lo riattivo.
Il microfono.
Il microfono da spento. Cioè ci dà il microfono spento. Però a noi risulta spento.
Che però addirittura vedo dove c'è i nostri nomi, no? L'elenco delle persone, che quando parlo si illumina a sinistra rispetto all'LP. C'è un puntino blu o 2 puntini a seconda del volume della voce.
Ah, però noi in questo momento, per esempio, il tuo microfono risulta spento, cioè noi lo vediamo disattivato.
Adesso ho provato sia col microfono.
Questo che è disattivato.
Sia
Che
con
fai?
Perché vedo, ovviamente ho dato i permessi. Ah, aspetta, che non sia il firewall.
Vediamo.
Aspetta che lo butto giù. What about now? Can you hear me?
No.
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 Che lo spengo e riaccendo.
Ecco, forse sì, Luca. Ok.
Aspetta che proviamo anche con...
Ok.
You can share.
Ora? Si sente?
Yeah. Yes, Luca.
Perfetto. Thank you. Okay. Yes. We are seeing LP. Okay. Let's share the screen.
Marina è collegata, Marco è collegato. Food. Adesso sarà questo. Quarto, Martina è in presenza. Aspettiamo che ci minuti e iniziamo perché
Ok.
We are already online.
Luca?
Yes.
Ok, che dite? Iniziamo? Sì, ok. Okay, we start with the first presentation. The title is Integrated Geophysical Study at the Colonel Henry Anderson Moshpit Burial Memorial, Valletta, Preliminary Results. The author are Sebastiano D'Amico, Luca Pirotti, Emanuele Codica, and Luciano Galone, and the presenter is Luca Pirotti. Okay.
Okay, thank you. Yes, this is a work done within the Department of Geoscience at the University of Malta. And with this note covers the geophysical investigations carried out at the burial memorial of Colonel Henry Anderson Moshpit, which is located within the Salutin Battery complex in Valletta, which is a quite famous location for the tourists. The main goal of, and of course a very important cultural heritage site of the town. The main goal of the investigation is to digitally reconstruct the internal part of the memorial as well as the external monument. And the derived 3D digital model was used to identify and locate cracks that need to be looked out, and also the large area of the square, the monumental square, was surveyed by means of a ground penetrating radar to map the subsoil. With this note, we present the very preliminary results of our investigation, and we will go through a brief introduction of the historical context of this monument, some concepts of the two main employed methodologies, that are the 3D reconstruction with the photogrammetric survey, and partially also with a portable LiDAR instrument, a low-cost instrument, and ground penetrating radar. Here you can see some images of the big island of Malta, the city of Valletta with the Great Harbor here, and the basin in which the site is located. This is the ceremonial square, and here up there are the Baracca Gardens that are an attraction for tourists. The Valletta Salutin Battery, as you can see by these images, is located in a commanding panoramic position overlooking the Great Harbor, and it is an integral part of the defensive system built after the Great Siege of 16th century. And during that siege, the Ottomans had occupied the mount of Valletta and installed powerful batteries there, which were conquered by the Order of St. John and converted time by time in ceremonial firing batteries devoted to for example, funerals or to celebrate wins in war, or to saluting dignitaries or important ships entering the harbor. In the 17th century, the covered loggia, a covered loggia was added for housing the knights, and it was destroyed. And in the 19th century, the upper section was transformed in the public garden that I already mentioned, the Upper Baracca Gardens, and which is the house of a series of commemorative monuments and plaques. The lower section houses the saluting battery itself, a rectangular platform with a continuous low parapet. And we can see here, and we can see also in the pictures from the surveys. And presently, the guns are firing for the noon, the 5 of the evening, and of course ceremonial occasions. The saluting battery was restored in 2004 for the initiative of the Fondazione Virtna, that is the Malta Heritage Trust. And in 2011, it comes to the present configuration with 8 working replicas of British guns for the ceremonial occasions. Here we see the monument, the funeral monument, and on the left the Upper Baracca Garden and the saluting battery square on the bottom. The geophysical investigation, I already said that were designed to document all the monument, including the ceremonial square and the funeral monument, and it is the workflow has included a photogrammetric survey and digital model reconstruction of here we see an image of the data acquisition of the funeral monument, which is which includes an underground room here below this monument, and the coffin of housing the rests of the hero. it's quite known the workflow for photogrammetric reconstruction from camera capture, alignment, binding, dense point cloud, mesh, and textured mesh, which is very important both for documenting the site as a historical documentation, but also in terms of diagnostics, because, for example, helped us to recognize fractures in stones and other elements of attention for the management of the site. Furthermore, I said in the introduction, well, the photogrammetric, the image collection was done with a digital camera and a LED energizer, because the room is totally closed, and we removed a lateral brick of stone to enter with this instrument, this pipe inside the room, and turning it to with the fixed camera and LED illumination to collect the photogrammetric data. And furthermore, it was used also with a portable LiDAR on the technology available on board of some manufacturers of smartphones. And the two kind of data sets were used jointly to have geometric information to scale the models, and to have detailed surface geometric surface information in terms of texture and geometry. The square, the monumental square, was investigated with stepped frequency GPR. With this image, we can see how is this instrument working, which is sending trains of monochrome energizations, and with the inverse discrete Fourier transform reconstruct a radiogram, which has the characteristics of optimizing the information and the frequency content at each depth. With this slide, we can appreciate the valuable information obtained from the 3D model reconstruction. And of course, there is also the help of GNSS survey to further constrain the dimensions. And you can see here the sections of the walls of the monuments, the coffin inside with the body of the military. And here we are looking down, here up, and we'll see next an enlargement with the detail of how this investigation is useful for the local management agency, because we have documented cracks and other elements of deterioration in the monument which need for intervention from that. And here I shift to the results, the preliminary results of the ground penetration radar. We can see the volumetric distribution of the GPR signals below the monumental square. And here we see the color bar and the histogram of the distribution of the samples. We can appreciate that most of the data are in this blue range. But we also see that we have some red here, even here, some red dots and large parts with green ranges of amplitudes. Shifting the palette to a monochrome black to red scale, we can start a brief preliminary but still useful interpretation, and which could lead further investigation. For example, we have identified an area to analyze in depth, and we have identified 3 areas that are here with a pattern, a green pattern, that comparing with historical aerial photo could be related to ancient pavement layouts. The darker red on the top, on the bottom, are probably linked to the structure of the bastion. And we can see also some modern infrastructure, like this dashed blue, that is a drainage system. Coming to conclusions, we can say that we have, of course, there is to underline the importance of the joint use of diagnostic disciplines and documenting disciplines like geomatics and geophysics, specifically for very important and precious and delicate sites. The capacity to reliable and deeply document precious assets, and to give information for further interventions, like detect internal structural defects, and also to point scenes of past uses, like the historical pavement remains, some cannonballs and ballets under the pavement, and other elements. We can say that excluding the main monument, we haven't found any underground rooms or large burials in the square. Thank you for your attention. Or eventually for asking information after the conference, you can contact me or the PI of the research. the leader of the geophysical team at the University of Malta, who is Sebastiano Davini. Thank you.
Thank you very much, Luca, for your presentation. Some question? No, only one question me. What's the maximum that you reach with the step frequency antenna? With a good resolution.
Yes, with a good resolution, I can see here we are looking at, well, this manufacturer in particular provides a very constrained access to experimental data, because we can export to data set named high resolution and low resolution, high frequency and low frequency. With the high frequency, we had seen good patterns at below 4 meters or even more, but we have interpreted only the few 1.5 meters, because at deep depth we detect some patterns, but they were too low constrained to interpret. So visually, you can see across the radiogram something that is coherent, but we had not enough information to give it a name. But with the high resolution, you can go down to 3-4 meters with good radiograms. I haven't seen the low resolution because given the specificity of the targets that were cannonballs or small elements, it was not our first target. Of course, we will look at them for structural investigation of the bastion, and is one of our goals for the next steps.
Yeah. Okay. Thanks, Luca.
Thank you.
Okay. The next presentation is investigating the Castello Archaeological Park, Cersosino, Italy.
Cersosimo.
Using a combination of geophysical prospection, aerial and terrestrial photogrammetry. The author are Marilena Cozzolino, Vincenzo Gentile, and Paolo Mariello, and presenter Marilena Cozzolino.
Okay, good afternoon. And yes, I'm going to present these preliminary results obtained here at the Castello Archaeological Park. The site is located in Italy, in the municipality of Cersosimo, that is a small village in Basilicata region. Is strategically placed on a hill with a view on the valley, the road networks, and the hydrological networks. As the main historical centers were built in ancient time in Italy. The archaeological site is placed in the southeastern part of the village, we have very few information about it because excavation were carried out in 1969, and results are unpublished, and just a report at the superintendency reports the first results, and the site here is supposed to be surrounded by defensive walls that are not known in the entire circuit, and it is supposed to have a quadrangular plan, irregular plan, and in this point was a secondary gate named Postirla was discovered, and it is the better preserved monument of the site, and further excavation revealed in 2 points of the city two main buildings that were named A and B. Building A is supposed to be to date to the 3rd century before Christ, and it should be a residential building in which there is a peristyle in the center and small rooms around it, and it was partially excavated. Building B is instead less known, and it is supposed to be to have an administrative rule. After the maximum stage of life of the Roman period, the site was abandoned, and it was interested by a return of habitation only in the Middle Ages. These are the only information that we have about the site. And in the frame of an agreement between the University of Molise and the municipality of Sersosimo, we started a project, and that is in the preliminary stages. In fact, the objective of this project was to add knowledge of the site, and in particular, we are going to try to understand the extension of the circuit and the internal division of the city. And we used a combination of geophysical prospection, in particular frequency domain electromagnetic prospections, and photogrammetry using drones and terrestrial cameras. As regards the geophysical prospection, data acquisition was carried out using a profiler, GSSI, And in order to maximize sensitivity to fluctuation and shallow conductivity, measurements were taken in continuous mode with vertical aligned dipoles. And we used frequencies between 2 and 15 kilohertz. And during the first steps of data processing, we used only the unique 15 kilohertz frequency that we then from which we obtained representation of apparent resistivity. And the acquisition was made each 1 meter, considering the sites of archaeological structures. At this step, no inversion was applied, and we plan to do it in next activity. And 5 areas, zones were prospected, as shown in this slide. After this, photogrammetric acquisition were realized using a camera for modeling the gate, that is from which we don't have any kind of documentation, and a drone to study all the site. The work for data processing followed the standard rules, and we used the AGSoft photoscan for data processing. So the steps were sparse point cloud generation, dense point cloud generation, georeferencing ground control points, and then 3D mesh generation. After this, the texture was applied, and digital elevation models and orthophotos were produced for interpreting data. And all results were processed datasets have been referenced and stored with a geographical information system, and several types of spatial maps have been created and arranged as 10 layers within the digital structure. Here there are some examples. We have cadastral maps, orthophoto, digital elevation models, and geophysical prospection, all compared with the previous recorded remains that are seen in blue. Here there is high resolution orthophotos that we produced regarding the gate that is built with big stones, and it is an important documentation not existing until now, and these products of course are very useful for architectural documentation and conservation planning. And going to the interpretation of these results, here geophysical prospection are to to the digitalization model. In white, there are some places that we can recognize considering the digitalization model. Here, for example, near the gate, we can suppose the continuation of known walls till the anomaly A recognized by geophysical prospection. In blue, here with blue coral, there is a low resistivity due to a pipe buried into the soil that disturbed all the results in this point. And we can suppose the presence of different terraces that level the topographical differences in the site. For example, in this point, the physical prospection highlights very high anomalies that has regular shapes, and maybe they could be the trace of buried structures, as well as the anomaly A. In conclusion, we present very preliminary results. There is a lot of work to do in this site, and the combination of these technologies demonstrated that in a very fast, rapid way, with the low-cost instrument, it was possible to enhance the knowledge of the site. Of course, we plan to integrate geophysical results with other techniques such as ground penetrating radar or electrical tomography, and we are planning to carry photogrammetry with a drone equipped with a LiDAR in order to remove the vegetation, even if also with the vegetation we were able to recognize some parts of the city. So that's all for me. Thank you very much for your attention. Thank you.
And you can go on. There are any questions online? Okay.
Thank you.
Luca,
Yes, thank you. Thank you, Marilena. Next presentation is integration of 3D ultrasonic tomography, photogrammetry, and mixed reality for the structural assessment of the marble statue from yeah, there is something with a shared screen. Excuse me.
Can you hear me? I'm here.
Yes.
Okay. Good afternoon, everyone. I'm Marco Vincenzo Aiani from the Department of Earth and Marine Science at the University of Palermo. In this presentation, I will show integrated the workflow developed for the structural assessment of the marble state of Caino by Domenico Trentacoste. The work combines three components: a 3D ultrasonic tomography, photogrammetric model, and mixed reality visualization. The central idea is simple. We do not want only to detect possible internal defect. We also want to represent the diagnostic result inside the real geometric of the artwork. In a way, the conservator can be inspected directly. The starting point of the study is the spatial conservation problem. When a museum plans allow a transfer or any movement of monumental artwork, it needs objective information about the internal condition of the object. For a marble sculpture, the surface may appear stable while the interior can contain hidden fracture, small cavities of decoration, plants, or area of mechanical weakness. For this reason, non-destructive testing is essential. The investigation must provide useful structural information without sampling or drilling or altering the artwork. Um, at the same time, the sculptures are not regular engineered objects. Anatomical geometry is complex with protruding volumes, curved surface, and irregular boundaries. If tomography is performed on a real computation grid, part of the reconstructed model may extend outside the real marble volume, create a boundary related artifact. Our goals was therefore to build a geometry constrained reduced ultrasonic velocity model of Caino and make the model directly explorable in mixed reality. This means acquiring a safe diagnostic dataset, reducing non-physical artifacts, and producing a result that can support observation planning in a spatially clear way. So the key message of this slide is this. And the problem is not only acquiring data, but translating those data into a reliable and usable diagnostic representation. We are in Palermo, in a historical center of the city, approaching the Galleria d'Arte Moderna, now as GAM. The transition from aerial view to the street level perspective brings us from the city scale to human scale. We are now in Piazza Croce dei Vespri, in front of the museum entrance. The GAM is housed in a monumental complex of Sant'Anna della Misericordia, one of the most significant culture space in Palermo. In this sequence, the video moves from a real urban context as a completed 3D rendering of the museum created with the last version of Unreal Engine 5. This passage is important because it shows the main aim of my works, connected the physical museum with a digital immersive environment. The final focus is the marble state of Caino, from Domenico Trentacoste, conserved in GAM. Our research uses 3D ultrasonic tomography, photogrammetric and mixed reality to investigate the internal condition of the sculpture in a non-invasive way. The object is to support the conservation decision, especially when evaluating the structural integrity of the artwork, and it is possible movement or loan. In this sense, the digital model becomes more than a visual reconstruction. It becomes a scientific tool for understanding, preserving, and communicating cultural heritage. A planned relocation made it necessary to evaluate the internal stability of the state before any movement. This was especially important because the state has set in a curled posture with complex anatomical volumes and many curved or protruding parts. This geometry creates two challenges. First, it's complicated the position of ultrasonic source and receiver in the state. And the second, it makes the tomographic reconstruction more sensitive to discretization error and edge artifact. There was also important conservation constraint. Direct contact between coupling gel and the porous marble surface. For this reason, a transparent PVC film was applied at the state before replacing the reference markers and position ultrasonic measurements. In these slides, you see I summarize the complete workflow from surface acquisition to diagnostic visualization. The first step was a high resolution photogrammetry used to generate a detailed 3D mesh of the state. The second step was to georeferencing of the ultrasonic measurement directly on the reconstructed surface. The first step was direct transmission ultrasonic acquisition, followed by manual first travel picking. The travel times were used as the input of tomography inversion. The fourth step was the CERT inversion with curved ray tracing in order to reconstruct the three-dimensional distribution of ultrasonic velocity. And finally, the regular grid inversion output was filtered within the photogrammetric boundary, and the resulted 3D velocity volume was exported to a mixed reality in augmented reality. The photogrammetric survey was a fundamental part of this method because we acquired about 300 high-resolution image from different waypoints and processed them in Reality Scan. Reality Scan is a software open source created by Epic Games, engine for video games, to obtain a pseudo point and texture mesh. The final mesh reproduces both the surface geometry and the texture of the state. More important, it allowed us to extract the coordinate of the 3017 markers point directly on the surface of the world. Sorry? I have noise. Okay. This was essential because ultrasonic tomography depends strongly on the accuracy of the source and receiver position in the state. If these coordinates are approximated, the travel time inversion may produce a spatial error that can be misinterpreted as real internal anomalies. The second role of the mesh was to define the physical boundary of the model. After inversion, the tomography volumes was clipped against the photogrammetric mesh. So the cell located outside the actual marble slab volume were removed. The ultrasonic acquisition was carried out in direct transmission mode. The instrumentation consisted for TDS 16 multi-channel system connected as a TSG 55 transmitter and RSG 55 receiver, operating at a central frequency of 55 kilohertz. For each signal, the first P wave arrival was manually picked. Then the dataset was checked through apparent velocity analysis to that inconsistent path or outliers could be removed before inversion. A total of 3017 surface points were available as a possible surface and receiver position from all possible combination. 520 search receiver paths were selected to ensure adequate coverage of the state volume. The sensor had conical steel tips, which helped to obtain localized contact on the curved surface of the state. However, because the marble surface is porous and historical valuable, the coupling gel could not be applied directly on the state. The protective PFC film solved this problem by separating the gel from the stone while maintaining acoustic coupling. Before performing the full tomographic inversion, we carried out a cinematic check of the dataset. The graph shows travel time as a function of the path length after filtering. The distribution is quite compact with a clear linear trend and only very limited number of outliers. This is already an important indication because a highly scattered cloud would suggest either acquisition problem, picking errors, or strong internal heterogeneity. The linear regression give a mean apparent p-wave velocity of approximately 5,000 meters per second. This mean velocity was then used as initial barrier for the model cell in the inversion. So this slide show that the raw kinematic behavior of the data already support the hypothesis of a generally compact material. The tomography inversion was performed using the CERT algorithm in GeoTom. The input data were the first arrival travel time, and the inversion aimed to reconstruct the internal p-wave velocity distribution. Curved ray tracing was used to account for possible refraction caused by velocity contrast. This is more appropriate than a purely strained ray approach when the internal model may contain a zone with different elastic properties. After the inversion, the output was still defined on a regular computation grid. This is practical necessity for the numerical problem, but is not ideal for a sculpture with a irregular boundary. For this reason, the grid was reinterpolated and clipped using the photogrammetric mesh. Cells outside the actual state, the global volume, were removed, and the final model became physically constant with the real object. Now, here we see the final tomography velocity model from two different perspectives. The color distribution is mainly green to yellow, indicating that most of the reconstructed volume has a relatively high ultrasonic velocity. Most of the state volumes exceed 3,000 meters per second, while very limited volumes fall below the range of 1,000 to 2,000 meters per second. In ultrasonic tomography of stone materials, such low velocity would typically be associated with surface degradation, hidden cavities, open fracture, or strong decoration. In this case, no clear tomography evidence or measuring internal cavities to ongoing fracture or severe degradation was observed. However, as a diagnostic basis for planning a possible relocation, the result is positive. The study can be interpreted as internally continuous and mechanically compact, with no major internal anomalies detected by investigation. The first step was the transposition of the tomographic model into a mixed reality environment. This is important because raw geophysical volumes are often difficult to read for non-specialists, especially when the objects are as a complex shape. In mixed reality, the user can inspect the diagnostic model at 1:1 scale, using interactive slicing to explore internal section of the state in real time. The mixed reality environment supports communication between geophysics, restorers, museum staff, and decision makers. To conclude, I would summarize the work in three main messages. First, from the diagnostic point of view, the Caino state show a generally compact internal marble matrix. The mean p-wave velocity is close to 5,000 meters per second. Most of the reconstructed volume is above 3,000 meters per second. No significant low velocity anomalies attributable to major defects were detected. Second, from the methodological point of view, photogrammetry is not only a tool for visual documentation. In this workflow, the programmatic mesh is used as a geometric boundary to filter the tomography model and reduce edge artifacts. Third, from the practical point of view, mixed reality transforms a complex volumic velocity model from tomography ultrasonic tomography into an explorable diagnostic layer. And now I'll show you in real time the state is I don't know if the hearing is a start. I don't know. Maybe not. Sorry for this little increase. Okay. Wait a second. Okay. Okay. Seen something? Can you hear me?
Yes, yes.
Yes? Okay.
Yes.
The same is inside my home right now. I have the wait. Okay. Is here. The now eyes you can see inside. This is a method approach for dissemination of results. For any question, I'm here for this. Thank you all.
Thank you, Marco. Any questions? I think most of the people are out now. Well, we can go on. Next presentation is statistical anomaly detection using LC cures, an application to geophysical time series from, sorry, I don't see Alexei Kozichev. I see you are, yes.
Yes. Good afternoon, dear colleagues. Can you hear me?
Yes.
Yes, so I will start. Hello, everyone. My name is Alexei Kozichev, and so today I would like to give a talk on the work that we did with Professor Aleskerov, who is also the head of the International Center of Decision Choice and Analysis at HEC University in Moscow. Professor Aleskerov would love to present this work by himself, but suddenly he couldn't come. So before moving to the main part of the work, I would like to give a brief introduction. First of all, I wanted to state that earthquakes are one of the most important natural hazards in the world, with severe impacts on human lives, on infrastructure, and on global economy. And the research in this field has been conducted for quite a long time, but nevertheless, there is still some room for improvement, and the problem of prediction earthquakes remains unsolved. On the next slide, we presented some statistical information so we can see the scale of the problem. We can see that each year happens around 17,000 earthquakes of magnitude from 4 and higher, and from 12 to 13 major earthquakes of magnitude from 7 and higher, which is very crucial because even one strong earthquake can lead to absolutely disastrous consequences. For example, an earthquake in China 2008 led to more than 65,000 casualties and to more than $130 billion in economic losses. So, on this slide, we presented some of the literature in the field, and the research has been conducted for more than 100 years, but without any significant success. But still, main approaches were identified, and now we can see that we can use seismic, geomagnetic, and other precursors to forecast future earthquakes. The next big group of literature focuses around regional studies, which shows the importance of local geological conditions, such as soil, sand, etc. And they also state that crustal deformations can be used as indicators of accumulating tectonic stress. And the last group of literature focuses around modern trends, which shows that there are many artificial intelligence-based methods which have great potential in improving prediction accuracy in the future. So with all of this being stated, we have the next problem statement, that despite the progress, the problem of prediction earthquakes still remains unsolved, which can be connected with the complex geophysical nature and with limited accuracy of existing models. So in this work, we propose a new approach using life cycle curves methods to analyze anomalous ground displacements as potential earthquake precursors. We use 5 minutes horizontal motion time series, and we use earthquake records from USGS catalog. And our goal is to detect anomalies from this data series. On this slide, we presented some of the information about the input data that we use. On the left part, we can see the time series from the exact GPS station, and we can see that this GPS station captures data in 3 directions, from north to south, from west to east, and on the vertical component. And on the right part of the slide, we can see the map of GPS station. On this slide, we presented the original construction of life cycle curves method, which was originally implemented by Aleskerov and Golubenko and future developed in the work of Aleskerov in 2009. So to calculate life cycle curve at exact moment t, from the top, we need to take the sum from the point t to the end of the time series, and from the bottom, we need to take the sum from the very first point to the last one. So now I would like to give some of the examples in original construction of life cycle curves and how does it transforms data series. So on the top part of the slide, we can see raw data, and on the bottom, we can see the results of implementation life cycle curve methods. Here are some more examples. We can see that on the left part of the slide, the consumption was a little bit steady in the very beginning, and it started to decline to the half of the time series, which resulted in life cycle curve going below the level of the diagonal. Contrary to the right side, we can see that in the very beginning of the time series, there was a huge spike, which resulted in life cycle curve going above the diagonal. Here are some more examples of consumer behavior implemented by life cycle curve: churning customer, growing customer, and a stable one. So now let's speak more precisely about the application of the life cycle curve methods for analyzing earthquakes. Here we present the data. We use catalog from period 2004 to 2025, and we work only with earthquakes of 6 points and higher. So we apply the next criteria, for example, presence of at least one GPS station in the vicinity of an earthquake, and the distance from the epicenter to the GPS stations should be not more than 50 kilometers. And there is also a criteria of absence of prior seismic activity and the data series of a 4-day GPS station observations. So after applying all of these criteria, we are left with 196 earthquakes. And to verify the model performance, we also use column data series, and we work with the same unique GPS stations which we got on the previous step. So we apply some of the criteria which are also presented on the slide, and after all of this, we are left with 104 column time series of 4-day complete windows of continuous GPS data. So now I would like to present a case which happened in Costa Rica, and it was an earthquake with magnitude of 7.6 with the depth of epicenter of 35 kilometers. And there were 2 GPS stations connected with this case. The first one is EPSA, which is located at approximately 30 kilometers, and Puch, which is located at approximately 6 kilometers. So we got the next results from the station Puch, which is closer to the epicenter. We can see 4 curves, which represent different days before the earthquake, and we can see that the blue line in north-south direction showed a very strong anomaly. It was approximately 10 hours before the actual earthquake. So to evaluate the method's performance, we use quite traditional metrics, for example, probability of detection, false alarm rate, and critical success index. The formulas are presented also on the slide. And after all of this, we are left with the next results. We tested different threshold parameters from 0.09 to 0.15. And at the minimum tested threshold of 0.09, we got probability of detection of 82% with a comparative false alarm rate of 29% and critical success index of 62%. We can see that with the increase of threshold parameter, the metrics start to decline, which is quite obvious. And now to the conclusions. We would like to state that life cycle curves reveal statistically significant anomalies before the major earthquakes analyzed in this work. We got maximum probability of detection of 82% at the minimum tested threshold. And there is also some of the important insights, for example, that the detection depends on the density of the GPS network, and anomalies can appear in any of the ground displacement components. Also, the timing of anomaly occurrence varies. So that's it. Thank you very much for your attention. I would be happy to answer all the questions.
Thank you, Alexei. Is there any question? I have one. Did you already evaluate if this approach is could be applied also to satellite radar displacement?
Yeah, we actually tried to use this approach for permafrost, but this is very recent direction for us, and we are currently in the progress of working in this. So we started with the earthquakes. Yeah.
Thank you.
Yeah, thank you very much.
Okay.
Yeah.
We are present, and the next presentation is the code overcoming the exception bottleneck in the small vision language model, computer science education. The author are Martina Iannaro and Maurizio Gabrielli, and the presenter Martina Iannaro.
Okay. Thank you for everyone to be here. And my name is Martina Iannaro. I am from the University of Bologna. And together with the co-author and also supervisor, Professor Maurizio Gabrielli, to present our work. The title is The Code Overcoming the Perception Bottleneck in Small Visual Language Models for Computer Science Education. I will walk you through the slide, trying to explain the motivation behind this project and also the evidence that support our finding. So, the main topic is downscaling intelligence that in literature is like the trend to that enable the deployment of a small visual language model on consumer-grade hardware or edge devices. This opens up an opportunity in computer science education because it gives the opportunity to build a personalized offline and privacy perceiving intelligence tutoring system. So the ethical core behind this work is to have all the inference on device. So on device to have like the ethical core are two. The first one is to guarantee the student privacy and data sovereignty, and also to have all this tutoring system on the low resource environment. So the core challenge is the fact that when we speak about computer science education, we are inside a technical education domain. It means that a lot of information are inside very heavy visual data. I'm speaking about like formal diagrams, pseudocode, or memory maps that are usually inside the textbook of programming languages. So the problem here is that if we want to have like an intelligent tutoring system, but we want it on device, we have to downscale the model, so the small visual language model. But the problem is that downscaling intelligence means to have like a regression in the capability of the models. So our goal here is to overcome the perception bottleneck via visual linguistic decoupling. So to go deep in the problem, we speak about downscaling asymmetry. So starting from the downscaling intelligence, and we have like a literature paper that is of this year, so 2026. In literature, they say that when we have like a small visual language model, so we have like a downscaling of in parameters of this model. It means that we have a regression in capabilities, but it's not equally from visual and textual point of view. It means that the model maintains its capacity to have like linguistic so it remains intact, but at the same time, so we have a collapses in visual perception. So this is the main problem here, because if we want to deal with images in computer science education, it means that we have to change the way of representing the visual data that are the main informative elements inside the textbook of computer science education or programming languages. So from pedagogical point of view, there is also this theory of dual coding theory, in which this dual coding theory say that is a pedagogical theory, one of the foundation pedagogical theory, that say that when we have this type of abstraction, the human brains need to process the information, the visual and textual information in the same time, so synchronized. It means that if we have like a misreading of image by the model, we have like we break the reasoning chain. The key takeaway is that the bottleneck in the small visual language model is primarily a perceptual limitation, not a cognitive one. It means that the model is able to reason, but it became like more blind. So when we downscale it, so we have like a perception collapses. So we propose this framework, the code, that is a training-free implementation of the extract plus think paradigm that is inside the cited paper said before. And in this framework, we have this, we start from extracting the data from the textbook that is named Principle and Paradigms. And we extract in two stages the data. The first stage is the textual one, so we extract all the narrative textbook using PyPDF loader library. And in the second stage, we extract also the images using a structured library. So at this point in the code, we apply the extract plus think paradigm. It means that we transform each image in a VCE. It means like a visual semantic extraction. It means that we don't have anymore an image in the pixel row, but we have structured text-based descriptors. So we bypass the bottleneck of the visual encoder. So here in the formula we have that we concatenate the text extracted at stage 1 and the VCE of the images when we have these images, and we encode it and we put inside the retrieval system. So we have like the drag, and We have like a different pipeline here just to have like to compare these techniques. So we have like the first one is a text only RAG. It means that we have only the textual data, so the data extracted in stage one. So we have just paragraph text chunks that are embedded inside the retrieval system. On the second, we have the multimodal native RAG. It means that we have the raw image pixel that are embedded inside the retrieval system. So here we have the text and the images, and we use like clip embedding model. And the last one that is the code is the multimodal VCE. So it means that we have here, as we said before, not anymore the pixel, but the description of the images. The description of images are generated by like an oracle offline that in our case is GPT-4o. And so I use a different model. All of these models are downloaded locally, so via Llama. I use the Moondream 2, that is the lower bound because it's 1.6 billion parameters. The second is Lava Phi3, 3.8 billion parameters. Lava V1.5, it is 7 billion, and 2.5, it is also 7 billion like Lava, but in a different architecture. So I started from the, our idea is to have like a tutor that was based on our course textbook, that is Programming Languages, Principles and Paradigms. And so we started from zero data. It means that from this textbook of the University course of Bologna for programming languages, we took both text and images, and I built like this benchmark, are two benchmarks, but are at the same time. I generated it through GPT-4o, so it's a synthetic benchmark. And but the first one is like a subset of 15 items of visual question answering. Is human validated. While the second one is 1,000 items generated by the data of this book. So at the end, the idea is that we created these two different benchmarks just to test the perception bottleneck on the computer science specific visual structures. This is a case study to make it a little bit more clear, because in the textbook usually we have this type of images when we speak about programming languages or computer science education. So, for example, this one is an image of abstract machine inside the book. And we can see here that, for example, if we have like the answer generated by the baseline, that means the multimodal native RAG, we have like an answer that is not related to the image, not to this image. So just mentioning like airline process management tool, but it's like blind with respect to this image. While the code answer citing like elements that are image, that are inside the image, like doc or lookup ship, that is element inside. While on the right part, there is another example here, and we can see here that it's like the baseline answer, like say that the pointer seems to reference a specified location. So here it means that it's not blind, the image is visible for the model, but it's not able to understand very well. So it's like misreading the image. The code answer in the right way. So we can say that applying a decoupled extra plastic approach, the code bypass the perception bottleneck, recovering the exact variable addresses and the logical gates. Also, I use different benchmark to have like a cross-domain generalization benchmark to see if this approach makes sense also on other type of benchmark, multimodal benchmark. that are more or less similar to the one that we created. So I tested on Science QA, Chart QA, and MM Star. And evaluation metrics, we have like open-ended visual question answering. It means that we need like NLP metrics for the evaluation, and I use Rouge L, but it's just for the sentence structure quality, while BERT score F1 is the one that can give us the answer, can give an evaluation on how much the got answer and the generated answer are semantic aligned. And also for the 50 VQA benchmark, so the one that is human validated, we made like a categorization of the items. So we try to categorize if one was a question answering was like affected by the perception bottleneck or not in the answer. And also we have a ablation study dimension, like task complexity. So we have like each items in the benchmark is divided between easy, medium, or hard complexity. It means that hard, for example, is when we have when the question is related to different part of the image. So it means that the model has to understand many elements inside many labels and how are connected inside for example, the diagrams. And also a division between visual and textual. It means that sometimes we don't have the image or don't need the image to answer, because when we took the data from the textbook, we don't have like a balanced data set, because we have a lot of text and few images inside the textbook. So here I reported just the model that outperformed the other. This is Lava 7 billion for simplicity. And so we can see that the number are very similar, but for the code, on both benchmark, considering BERT score F1, we have more or less we have the higher number, and also at the second position there is text only RAG that surpassed the clip RAG, that is the native multimodal RAG. So it means that apart the code, it's better to have only text and not the embedding of the pixel of the images. So here is like the ablative analysis that we said before. And here we can see that, for example, for Moondream 2, that is the model made by 1.6 billion, we have like this number, 6.38 for the visual type for the code, while for clip RAG, that is the multimodal native RAG, is 0.63. It means that it's like it was like a collapse on the code, but the code here is just text. So it means that it's like overwhelmed by textual information, and so it's better in this case to have the embedding of the pixel. Okay, so here, like in the chart, we see the same, because we can see, for example, here in visual that it's like a collapse of the model for the code, that is the blue line, and we see that it's a collapse here, but around 3.8, that is the second model, that is Lava 3 is like going up 100 times. So it means that in this case, the code is like a little bit better than the other configuration, but at the same time, we need to have like a reasoning threshold that is around 3 billion, has to be like above 3 billion and overall. Also, we can see like the same of out of domain that the other benchmark that we see before, that I said before. We can see here that when we reach this reasoning threshold here, we have like the code better than the other configuration for 7 billion model. So this one is the error distribution shift, on the 50 visual question answering, so on the small benchmark, the human validated one. And we have like, we can see that with multimodal native clip, we have a lot of perception failure, while for the code, just the 4%. While the other ones, so linguistic hallucination and reasoning flow, remain more or less the same. So also here, this chart is divided in left and right, because we have on the left we have the items divided for visual, and on the right for textual task. So on the left part, we have every time the fact that the code is like collapsing at Moondream 2 and go up around 4 billion. While on the other part, it is only textual, it's more or less stable. All the lines are more or less stable. It means that we have like this reasoning threshold, and we have to, the model are overwhelmed by text. So the reasoning stays flat and the perception collapses at Moondream. So also the core takeaway are that on a public benchmark, we see also that the code has like a better performance also on the other out-of-domain benchmark, very small number, but it's confirmed it's a little bit better than the native multimodal or only text RAG. In particular on chart QA, the benchmark is more similar to our benchmark, and also there is like architecture agnostic benefit, because the gain is also on Lava 7 billion, also Qwen 7 billion. So the conclusion is that the perception bottleneck is solved, and this is like a solution in computer science education, because give us the opportunity to have like an intelligent tutor system on low resource environment, and also can guarantee the privacy, the data privacy of students, having so on-device inferences. The future research direction, the first one can be like to not to move the extraction, the visual extraction, so the generation of VC, that is the textual representation of the images on local, so on the device, rather than asking and using API dependencies. And the same way can be from pedagogical point of view, pass from static QA to a multi-step conversation system.
We have time for a quick question. I don't know if online. Yeah. Okay, one. Thanks very much, Martina, for your presentation. And I want to thank all for your presence and for your beautiful presence. And I hope to see you next year. Okay. Good afternoon.
Yes.